Okay, so since I'm out today and class was canceled on Monday due to the power outage, this is actually going to be over lesson 12, and then we'll pick up with lesson 13 on Friday. What this means is moving into our next test, that overflow day will be consumed, and we will not have an overflow day on the schedule, but the test date will not change. So you do have some some strongly recommended questions on here for you. For the most part, chemical equations, you guys can look up definitions about that. But what I do want to make sure you hear me say out loud in words is how you talk about chemical reactions. So in this case, if I was describing what was happening, I would say that 2 hydrogen molecules react with 1 oxygen molecule to form 2 water molecules. Okay, now that's how I would say it to someone else who was going to need to know that information. Now, if I was going to communicate that as a chemical equation, I would write it out like this that you see here. Okay, so reactants and products. Reactants are always on the left. They are what is reacting, and the products are always what is produced. So they're usually going to be on the right-hand side of the arrow. Okay. Some other things that are important are the plus sign and the arrow. This tells me which direction the reaction is going. Okay. So we've seen these before. So just to review, the solid, liquid, gas, and aqueous. Aqueous is anything where the solvent is H2O, and typically the main liquid we're going to see is water, though there are some other examples of liquids, but the most common is water. So what does it mean for an equation to be balanced? Well, it means that the law of conservation of mass is met. That's one of it. And then we're also going to say that in the end it's going to be charged balanced, and we'll talk about what that means. Okay, so if we look back up here, we had 1, 2, 3, 4 hydrogens, 1, 2, 3, 4. So that's balanced, mass balanced on the left and the right, and then 2 oxygens and 2 oxygens, so it's mass balanced with oxygen as well. Now, because hydrogen and oxygen and water are neutral, this is also charged balanced. So when balancing an equation, why can you not change the subscript? This is really important because I find that people tend to do this and it's not correct. If you change the subscript, you're changing the identity. Okay. So for example, H2O and H2O2 are not equivalent. So we're not going to change the subscripts. It's not correct. Instead, what we are going to add or change is called a coefficient. Okay. And the coefficient, if we look back up at our example here, the coefficient was this 2 in front. Okay, those are coefficients. They're large numbers that are going to be in front of the formula. Okay, so those we can change and or add. And then we'll talk about molecular, complete, and net ionic when we get down to the example question. So if there's anything else not filled in, or you have more information filled in, that's great, but this should hopefully give us a start on our pre-lecture questions that I ask you to do before you come to class. So the first thing we're going to do today is balance chemical equations. You're probably going to need more space than what I gave you if you printed it straight off of Canvas, so you might need an extra piece of paper. Now, if you have a method for balancing chemical equations, then keep your method. I'm fine with that. If you don't have a method, I'm going to walk you through some examples. And then if this method works for you, then you can feel free to use it. So we know that we need to balance it because it tells us to balance. So from here on, from the rest of the class after this lesson, you should always check that the equation is balanced. We cannot assume anymore that it is, unless it says the following balanced chemical equation. So the way that I do these problems is I kind of take what I call an inventory of the left, the left and the right, and I use my subscripts to tell me that I have 1 phosphorus, 5 chlorines, 2 hydrogens and 1 oxygen on the left. And then I'm going to do the same thing for the right, but I'm going to keep my atoms in the same order. That way I can very easily compare left to right. So I see that I have 1 phosphorus on the right, 1 oxygen, 3 chlorines, make that 4 chlorines. There are 3 here and 1 here. And then I have 1 hydrogen. Okay, so once I have my inventory of my my atoms, I'm going to go ahead and start to balance. Let's pick a different color. So in this case, it looks like my chlorines are not balanced and my hydrogens are not balanced, and but everything else for now is. And so what I need to do is adjust the number of hydrogens and chlorines on the right, and the easiest way to do that is to add a 2 in front of the HCl. And this now will give me, because the 2 will distribute to the chlorine and distributes to the hydrogen, just like algebra. So this gives me 3 plus 2 chlorines and 2 hydrogens. So now I'm balanced. So my final balanced chemical equation without the phase states is this. Okay, so this tells me I have 2 hydrogens and I have 2 chlorines. It's the same thing as when we had, let me think of a better example. Okay, it's the same thing as this 2. This 2 distributed to the 4, and it also distributes to the phosphorus 1. Okay, so coefficients and the subscripts outside parentheses are very similarly used. Okay. All right, so the next one, we have copper plus nitric acid makes copper nitrate plus water plus NO. And so I'm going to start off with my inventory. So because the 2 is only outside the nitrate group's parentheses, it does not apply to the copper. So I have 1, 2, 3 nitrogens, because there's 2 here and 1 here. And then I have 6, 7, 8 oxygens. Okay, so the number one mistake that people will usually make is not accounting for the correct number of atoms in their first attempt at the problem. Okay, so I can see here that I have I'm short on the number of hydrogens, on the number of nitrogens, and the number of oxygens. So in this case, I need to have a total of 8 oxygens on the right, and I need to have, and I only have 3 on the left. So one of the easiest things to do when we have this kind of problem where I have an even number and an odd number, okay, and then there's an odd here, and then so it's going to end up being a little bit more complicated. But what I can do is I can take this 8 and I can put the 8 there because I don't really have another number in common between them. But if I take the 8 there, this is going to change this to 8, 8, and 24. Okay, so it kind of seems like a lot, but let's see if we can make it all work out. So now my next thing is to adjust the number of nitrogens. But part of the problem is I have a nitrogen there and a nitrogen there. So what I'm going to do to help adjust the number is I'm going to put a 3 here. Okay, if I put a 4 here, I'm going to have too many nitrogens, but if I put a 3 here, 2 times 1 times 3 is 6, plus this one, which is 7. So it's close, but not over. This is going to give me 3 coppers, and this is going to give me 2 times 3 oxygens times 3, which is 18. Okay. Now, the other one that's not balanced is now my copper. So I'm going to put 3 here on the left to balance that out. So now this is balanced. And my hydrogens are not balanced. I need 4 times as many on my right-hand side. So I'm going to add a 4 in front of the water. This now gives me 8. And now if I look at how many oxygens I have 18 in the copper nitrate, plus 4 in the water, plus 1 in the NO, and that's going to be 18 plus 4 plus 1 is 23. So you can see that I'm short 1 nitrogen and I'm short 1 oxygen, which means this last little group here is going to get a 2, and that will balance out the rest of my equation. So this is kind of a more difficult example, just because we started off with a very large number in one of our inventories, which was the 8 compared to the 3. So when we have numbers that are that far apart and they don't have another common denominator like twice as many or 3 times as many, you should just take that large number and move it to the other side to balance out that even number, because multiplying 3 times 8 automatically gives me an even number, which allows me to work towards balancing both sides. All right, CP opportunity for, actually, let's do one more. We'll leave number 4 for a CP opportunity, okay? Because we're going to have lots of problems on this one. So hydrogen and iodine, this is going to seem like a really easy example compared to the last one. I need twice as many hydrogens and iodines, so I'm going to put 2 on the right. And now it is balanced on both sides. So final answer. Okay, so CP opportunity on Friday, the very beginning of class. If balancing chemical equations is not one of your strengths, I recommend practicing it as much as you can between now and the test, just because we're going to use balancing chemical equations in more ways than what we just saw here. We're going to build on it in specific ways with stoichiometry, so make sure you know how to balance. All right, now the other thing that we're going to learn in this lesson is how to take information we learned in previous lessons about nomenclature and typical words we see in chemistry to write a balanced chemical equation. So in this case, it says that potassium chlorate, so in this case we have to know potassium and chlorate, and we know that it's solid, so we have to know how to write that. And it decomposes, so that's the arrow, the reaction happening, to form solid potassium chloride and diatomic oxygen gas, right? Because oxygen does not exist by itself, okay? So now to balance it, I have 1 potassium, 1 chlorine, and 3 oxygens, 1 potassium, 1 chloride, and 2 oxygens. So same thing as the one where it was 3 times 8. I'm going to take the 2 over here and the 3 over here, and now all of a sudden I'm going to have 6 oxygens, so those are balanced out, and now I have 2 potassiums, 2 chlorines, and I need to add a 2 to this side to balance it out. Okay, so that taking the odd number and the even number and switching sides with them is a really useful strategy. Okay, so this satisfies all parts of the question that it asks us to do. Now this one says when solid sodium chloride is added to aqueous sulfuric acid. So you can see now that if you didn't understand nomenclature back then, it's going to be important. It says hydrogen chloride gas and aqueous sodium sulfate are produced. Okay, so produced, that means that there are products. And it's a gas plus sodium sulfate aqueous. So now I need to balance it. I need 2 sodiums on the left, and then now I need 2 chlorides on the right. I have 2 hydrogens, 1 sulfur, 4 oxygens, so everything else is balanced. Okay, so very similar to what we did up here, except we're adding an extra layer, which is taking the nomenclature that we learned in previous lessons and now applying it to building these equations. All right. The next thing we're going to talk about is from the balanced molecular equation, which is what we did up here. We're going to take the complete ionic and net ionic equations for the following 2 examples. And then I have these rules here. Okay, so these are for you. I took them from the book and summarized them in shorter words and put them here. So you need to know these. Okay? There's no other way around them to do these problems but to know the rules. So the rules are that something that is solid, liquid, or gas is going to stay together. It will not break into ions, meaning it's going to stay as a molecule. In the complete ionic, which is the first type of problem equation we're going to write, all aqueous compounds are written out in their ionic form with their charge. So we're basically going to break them apart into their ions. Coefficients that are on the compounds in the molecular equation are the same value in the complete and net ionic equation. Meaning, if I have, let's say up here, I had 2HCl, this is going to break apart into 2 plus 2 chloride. Okay, so the coefficient belongs to both of them. And then the last one is that we're going to eliminate all spectator ions in the net ionic equation, which is the second one. Okay. The rules for the spectator ions, present on both sides of the equation, present in the exact same phase and charge on both sides. Okay, so we're going to identify spectators and then rule them out and write the net ionic. So let's practice. So looking at this, I have lead nitrate plus sulfuric acid makes lead sulfate and nitric acid. So in this case, according to the first rule, this is going to stay together. Okay, that's according to rule number 1. I'm not going to break it apart, but everything else is aqueous. So we need to break it apart into its specific ions. So basically we're going to unpack. The lead has a 2 plus charge. I have 2 nitrates because that's what this subscript here tells me, is there's 2 separate nitrate groups in that compound. Okay, and then this is aqueous. Plus 2 protons, aqueous, plus SO4, 2 minus, aqueous. Okay, so in this case, I've taken care of all 4 species on my left. And remember, sulfate nitrate groups are polyatomics, and polyatomics stay together. We do not break them apart into nitrogens and oxygens. Now I've got my arrow. Now my lead sulfate, we said, gets to stay together. So I'm not changing it. And then I have my nitric acid. And my rule number 3 says that the coefficients on the compounds and the molecular formula are the same in the complete and the net ionic. Okay, so this is what I call my TIE, my total ionic equation. Okay, so this answers the first half. Now to go from the TIE to the net ionic, we need to subtract my spectator ions. Okay, equals the net ionic equation. So if I'm looking at the one equation I just wrote, I'm looking for things that are the same on the left and the same on the right. So in this case, I have 2 hydrogens, they're in the same phase, I have the same number of them, and they have the same charge. Those are spectators. My 2 nitrates are both aqueous, they have a 1 minus charge, and I have 2 of them. So these are my spectators, the ones that I have written lines with under pink. So now when I write my net ionic equation, all I'm going to write are the things that are not spectating, which is lead 2 plus aqueous plus sulfate aqueous, which yields lead sulfate solid. So this is my net ionic. Okay, so we have 3 different types. We have the molecular, which was here, the total, and the net ionic. Guarantee this will be a short answer question on your test. Okay, from molecular all the way to net ionic. So let's practice it again. In this one, I have calcium carbonate, which is solid, so it's going to stay together. Calcium sulfate, solid, stay together. Carbon dioxide, gas, will stay together. And water, liquid, will stay together. So the only thing that's going to ionize is sulfuric acid. So I'm going to have 2 protons, very similar to before. And my sulfate. Okay. Then I'm going to look for my spectator ions, and I see that calcium carbonate, there's no calcium carbonate on the right. There are no protons on the right. There's no sulfate by itself on the right. There's no CO2 on the left, no calcium sulfate on the left, and no water on the left. Therefore, my total ionic and my net ionic equations are identical. When there's no spectator ions to cancel out, then it's like the empirical formula. When there wasn't a least common denominator from the molecular formula, then we said that the empirical and the molecular formulas are the same. Okay, and it's the same thing here. If there's no spectators to cancel out, then we don't have a different net ionic equation. Okay. However, the total ionic equation and the net ionic equation are distinct from the molecular equation, where everything is written as molecules. Okay. Another one to practice, I think Sapling gives you 2 questions on writing these, but the best way to get good at these is to write them on paper first, because your test is not electronic, your test is written. So if you're only typing them into the computer, the first time you're expected to write them out, it can be kind of difficult. Okay, so make sure that you practice writing these out. All right, important types of reactions. This is the last thing we're going to do on this lesson. Okay. So we're going to talk about 5 different kinds of reactions, and then on Friday we're going to learn some more specific types. Okay. So all of these give you the definition of the different types right here. So it's nice and easy. The synthesis is also called a combination reaction, and it's the combination of 2 or more substances or reactants to form a new substance or a product. So in this case, it's usually A plus B makes AB, or sometimes is written C to show that it's something brand new. So write the balanced chemical equation for the reaction that occurs between iron and sulfur to form iron 2 sulfide. So in this case, iron in its elemental state plus sulfur makes iron 2 plus, and then remember sulfide is 2 minus. So when they swap charges and we take the least common denominator, it's iron sulfide. Decomposition, on the other hand, is the opposite. It's the formation of 2 or more substances from one substance. So the example that it wants us to do is write the balanced chemical equation for the electrolysis of water to form oxygen and hydrogen. So we're going to start off with water, form H2 and O2. Remember, these are 2 examples of our diatomics. So when we get ready to balance it, we add a 2 in front of the hydrogens, and now it's balanced. Kind of a generic. So these are, oops, sorry guys, kind of opposites. All right, so single displacement is the exchange of a cation or an anion to form two new substances. So it's kind of like swapping dance partners, if you will. Okay, so sometimes, to write one generically, if C is an anion, they're kind of swapping like this, okay? But it doesn't always have to be C swapping for B. C could swap for A. It just depends on the nature of C. So this says write the balanced chemical equation for the reaction that occurs between aluminum chloride and zinc. Okay, so you have to know a little something about zinc, and that is it a cation or an anion? Okay, now we know that zinc is a metal, it's a transition metal, so it's most likely going to want to be a cation. And if you remember from lab, zinc chloride was what we produced in the empirical formula lab. Okay, and so zinc usually always wants to be a zinc 2+. I would have to give you that information on a test because I'm not asking you to memorize the transition metal oxidation states. And so now we need to balance it. We have 3 chlorides on the left, 2 on the right, so I'm going to use my opposites rule and put a 2 in front of the one that has a 3 in it and a 3 in front of the one that has a 2 on it. Now I have 6 chlorines, 6 chlorines. I need 3 zincs, and I need 2 aluminums to balance out the rest. Okay, this is called single displacement. Sometimes it's also called single replacement. It just depends on the preference of the author of that text. So you'll see different terms in your sapling homework. Now, double displacement is going to be the exchange of both the cation and the anion to form two new substances. So something like A and B plus CD, and then they're going to swap. So everybody swaps dance partners. A and D come together, and then B and C come together. Okay, so here we have calcium carbonate and hydrochloric acid. So to solve this, we have to know something about metals and nonmetals. So metal, nonmetal, polyatomic group with our hydrogen. Okay, so the cation and the anion are going to come together in the different pairs. Okay, so now I'm going to have calcium chloride and H2CO3, carbonic acid. Okay, so the reason why the 2, because calcium is 2+, carbonate is 2-, so when they combine with the +1 and the -1, now we have subscripts. Okay, so now we need to balance it. I have 2 chlorides on the right, and 2 hydrogens on the right, and I need to have twice as many on the left. So this is my balanced chemical equation. So also double displacement, often called replacement. Now combustion is a specific type of reaction where it's exothermic, meaning heat is released, that occurs between oxygen and a hydrocarbon. Okay, usually the products are CO2 and water. So in this case, this tells me to write the balanced chemical equation for the combustion of naphthalene, and it tells me that naphthalene is C10H8. I have to know that it's combustion, and in order to predict that the other reactant is oxygen, and then because it's combustion, I can predict that my products are CO2 and water. So you have to use your knowledge of combustion to predict the products and to understand that it's oxygen that's reacting. So now I need to balance it. I have 10 carbons on the left, so I'm going to give myself 10 on the right. I need to increase my number of hydrogens, so I'm going to put 4 here. And now I have 10 times 2, 20, plus 4 oxygens, so I'm going to put a 12 here to balance out and give myself 24 oxygens on the left. Okay, so this is my balanced combustion equation. So most of the time, this types of reactions that you see here, identifying the type, so it's normally multiple choice type question, or very similar type thing where it's, you have to read that this is the reaction occurring and what type is it. Okay, so I could give you which of the following is combustion and give you 5 balanced chemical equations to pick from, or I could give you an equation and ask you what specific type that one is. So sapling has lots of good examples. Make sure you work through them, and then because we're going to continue to add 2 more reaction types when we meet on Friday. Okay, so at the end, sapling homework, and then lesson 13 notes, and then bring your book, however you access it, to class next time, because we're going to look at a table that you need to work on memorizing the information off of before the next test. Okay, so it should be everything that you need. This will be a video that's uploaded on YouTube, so if you need to go back and watch it before the next test, I highly recommend that, but it'll be available to you after class today.